This is the last section for Chapter 3. So far, first section we've been looking at a group of data and we've been trying to figure out what's average, what's the mean, what's the median, what's the mode, basically what's average with all that data. Second section, we were talking or looking at how much does that data vary, because you can have two separate sets of data and you can have the same mean for both of them, but that data can be drastically different. For instance, the numbers 24 and 26, the average is 25. Okay, the numbers 0 and 50, the average is still 25. So sometimes the mean doesn't tell us a lot about the data, and that's why we look at the variance or the standard deviation, because that tells us a little bit more about how much that data varies. So you've got your average, what's the average of all that data. You got the variance or standard deviation. Both of those numbers measure variance. And now what we're getting into is looking at a set of data and then picking one piece of data and finding out where that lies. Okay, so we're looking at the position, this section. Okay, we're going to look at one of these things on the list, two of them, sorry, today. We're not going to get through the entire section. We will pick that up tomorrow night. So first thing we're going to look at is something called a Z score or standard score, but we will refer to it as a Z score all the time. A Z score, standard score is actually a really good name of describing what it is. It's trying to standardize a score. And so if you have two different scores in two different classes or from two different data sets, this Z score allows you to kind of compare the two. Okay, it's allowing you to compare apples to oranges. All right, the way that it's found out is two different formulas here. You notice that this one right here is for a sample, and this one right here is for a population. Okay, remember, X bar is the mean, mu is also the mean, S is your standard deviation, sigma is also your standard deviation. So same formula, just different symbols, because depending on if we're dealing with a sample or a population. So a Z-score represents the number of standard deviations a value is above or below the mean. A Z-score works for data that's normally distributed. So you cannot find a Z-score for every set of data. Okay, if that data, this is going to be a really bad picture, but if that data looks something like this and it's kind of got some skewness to it and it drags off, skewed to the right like that, Z-score will not work. Okay, what we are talking about is a nice bell-shaped, normally distributed set of data. So here's how it works. We're going to look at two different test scores, and we're going to find out which test the student did better on. So a student scored a 65 on a calculus test. It had an average or a mean of 50 and a standard deviation of 10. That student also scored a 30 on the history test, which had a mean of 25 and a standard deviation of 5. We want to compare her two test scores and find out which test did she score better on compared to the rest of the students. Reminder, this test score, this Z-score doesn't necessarily say you scored better. It just shows how well you scored compared to everybody else. Okay? Keep that in mind. It's compared to everybody else, compared to all of the data. So here we go. Finding the Z-score. Pretty easy to do. They considered this a sample because it was, I guess, just one class. Again, it doesn't really matter which symbols you're using. The formula is the same. So her test score was 65. That goes right here. That's the X value. The mean was 50. Standard deviation was 10. So we do all that. 65 minus 50 is 15. 15 divided by 10 gives us a Z-score of 1.5. So that means she scored 1.5 standard deviations above the average student. Okay? For the history test, her test score was 30. The mean was 25. Standard deviation was 5. So 30 minus 25 is 5. 5 divided by 5 gives us 1. Which test did that student score better on? Calculus is a higher score, and therefore she had a higher relative position in the calculus class. So actually, let me go back to what I said a little bit earlier. She didn't necessarily score better in calculus. She scored better compared to everybody else. That's what they're talking about here. The position, her position in the class was better for calculus than it was for history. Okay? If you have any questions on this, please write something down. I'll give you a second if you want to pause this and kind of take a look at it, but this really breaks down a normal distribution on the percentages that fall between, you see right here, this is one standard deviation. If you add these percentages up, it's approximately 68%. So that's why they say approximately 68%. It's not exactly, it's approximate. And even by getting approximately, I mean this is 68.26. If we add these up, that's an approximation. It's not exactly. Okay. We go 2 standard deviations out, that should be 95, right? We're talking about all these numbers added up. All right, make sure you're thinking about that. So this is showing standard deviations, either below or above. This, the cumulative percentages, if you start at 0 over here and add them up, we don't really use that too much. Percentiles, we will a little bit more. Z-scores go along with standard deviations. T-scores, standard nines, and percentages in the standard nines, we don't really worry about too much. Okay. Percentiles. A percentile is basically if you look at all the data and you try to group them into 100 different groups. Now, if there are 100 people, that means each group has one person. If there are 200 people in that data set, or 200 sets of data, each group would have 2 people. If the group only has 10 people, okay, there are 100 groups, but technically there are only 10 people, right? So you only have 10 groups. So your percentiles get a little bit bigger. But basically, think of taking your data, breaking it up into 100 different groups. They're all of equal size. Okay. A percentile rank for a piece of data represents the percentage of data that falls below. So if we give you you fall in, you get this with your ACT score a lot of times. If you fall in the 88th percentile, 88% of students scored less than you. 12% of students scored higher than you. Okay. Here's how you find your percentile. You take the number of values below X, X being whatever value, whatever score you got, add 0.5, divide it by however many values there are total, and multiply it by 100%. Okay, so here we go. Here are 10 students. So again, we don't have 100 pieces of data here, so your groups aren't going to have a full one person for each one. Okay. Find the percentile rank of a score of 12. First thing you want to do is take all the data and sort it. Okay, sort it from least to greatest. So here we have all that data sorted from least to greatest. We want to find where does a score of 12 fall. So we take our formula. There's your 12 right here. How many values fall below X? Count them up. 1, 2, 3. Sorry, I had to pause that. Okay, I'm back. How many values fall below x? 1, 2, 3, 4, 5, 6. 6 values fall below x. We add on a 0.5 to it. So we have 6.5 divided by how many values there are? There are 10. Okay, so we count it right there, 6 values, 10 total. Take 6.5 divided by 10, you get 0.65 times 100%. That gives you 65%. So what that means is that student did better than 65% of people in the class. Now you may say, wait a second. 1, 2, 3, 4, 5, 6. 6 out of 10 is 60%. They didn't do better than 65%. You're right. 1, 2, 3. 3 students do better. That's 30%, not 35. Where's that extra 5% coming from on both sides? Well, you have to think that this score takes up 10%, right? We didn't have 100 different groups here. We only had 10. So this kid is considered 10%. This one is 10%. This one, this one, this one. So we don't say that between 60 and 69% scored worse than you. We just use the midpoint of what this kid represents. This kid is in the 60s, all the 60s. So we use that middle number. And that's what that 0.5 is doing. As you get more and more pieces of data, each group is a little bit smaller. And so that little variation or that error on each side gets smaller and smaller the more data that there is. Okay, what if we are given a certain percentile and we want to find out what score matches that percentile? So, you know, you're going into college and then let's say a certain college, I don't think they ever do this, but if they would say you have to fall within the 80th percentile in order to get into our college. Okay, well, you might want to be curious, okay, what kind of a score is that? So here's same data. Again, we're going to put them in order from least to greatest. We're going to use this formula that figures it out. So make sure you put this formula in your notes. C is going to be that value that represents the percentile you're looking for. N is how many total values or total pieces of data there is. And P is the percentile that you're looking for. So we're looking for the 25th percentile. 10 is 10 pieces of data. 25 means the 25th percentile we're looking. We divide that by 100. So we got 250 divided by 100. That gives us 2.5. So we're going to look at the 2.5 piece of data. Well, where is that? Do we look at, you know, go 1, 2, 2.5, and go in between 3 and 5, 4? No, we don't want to say that, because if we say, oh, the score of 4 will land you in the 25th percentile, nobody actually scored 4. So we don't want to use a value that's not there. So what we do is we approximate. Okay, we say approximately the third. We're going to always go up on this. So even if it's like 2.3, 2.4, we're going to go up on it. So that's approximately the third value. 1, 2, 3. Approximately a score of 5 will land you in the 25th percentile. Okay. There's your formula again. And that's where we're going to end today. Write down any questions. We'll see you in class tomorrow.